I want to talk just a quick second about computational complexity. I mentioned it before. As we said, if your image is n by n and your kernel is m by m, or we'll call it w by w for sort of width, and it's easier to say w being different than n because exactly. Okay? So the question is, how many multiplies do we need? And we said before that we need n times w, or n squared w squared. Doesn't n squared w squared sound better than n squared m squared? Because when I say n squared m squared, you have no idea what I'm saying if I say it quickly. N squared w squared works. And that can get sort of big. So there's a cute little property. Sometimes your main kernel, your filter, can be created by convolving a single row with a single column. And when that's true, you can take advantage of the associative property in terms of how we do this. And this is what's referred to as a linearly separable kernel. So let me show you an example. So here we have a single column, and here we have a single row. And just think of zeros being around it. If I convolve this column by this row, I would get out this new H, which has 1, 2, 1, 2, 4, 2, 1, 2, 1 in it. Okay? So C convolved with R equals H. See, this is why we don't use my handwriting. Let's suppose we wanted to filter something with H. All right? So that would look like this. We have a function g that we're going to create by convolving f with h. But we said that C convolved R is the same as H, so that convolves F. And because of the associative property, C convolved with R, then convolved with F in order to get our new function, is the same as C convolved with R convolved with F. And the reason that's better is that I can do two column convolutions instead of one squared. So now instead of being w squared n squared, it's 2 times w times n squared. And that used to be very important when computers were not quite as fast, but it's still reasonably important because, for example, if w is, say, a 31 by 31, that's a factor of 15 difference, all right? So that's more than an order of magnitude. Anytime you can do anything that buys you an order of magnitude for not a lot of money, you should go ahead and make that purchase because orders of magnitude are hard to come by. So here's a nice way of doing that. So when we do various kinds of smoothing, etc., often we use linearly separable filters, and you can just apply them.